So this is video 16.4 of the packet. Remember last time we talked about how to determine whether a solution is acidic or basic. So if the hydrogen ion concentration and the OH hydroxide concentration are the same, that's neutrality, and that would be 1.0 times 10 to the minus 7th for each concentration. An acidic solution is going to have a higher concentration of protons, and a basic solution is going to have a higher concentration of hydroxide. What we're going to do today is look at all the rest of the equations on your reference chart. And a lot of this is review. I know you did this if you're a junior during COVID virtual school last spring, so I don't know how much of it we've remembered. But we can determine what's called a pH from taking the log of concentrations. What the log does is it allows us to take this huge range of possible concentrations and narrow it down to a scale of about 0 to 14. That's what's useful about the log scale. And every acid or base is going to fall based on their concentration and the log of it in that scale. And 0 is going to be the most acidic, and 14 is going to be the most basic. And so that is what taking the log of these concentrations will do. So let's look at how we use these equations. You have done this before. So again, all of these equations that we're going to look at are given to you in your formula chart. Here they are here. pH is equal to negative log H. POH is negative log OH. And then if I add the two together on the scale, because they go between 0 and 14, that if I take the sum of them, they will be no greater than 14. They will always equal 14. We'll talk about this right here in the next unit. So everything for the test that you have, the first test you have, will be everything from here up. This will be on the second test. Okay. So pH is defined as the negative log of the hydrogen ion concentration. Please watch this negative. It's really easy to miss that. Remember that as the hydrogen ion increases in a solution, the pH will decrease. One thing I almost forgot to mention, and that is sig figs. Okay, so for pH, it's going through this equation. How do we do sig figs in a logarithm? So when you do this, it says only the numbers to the right of the decimal are significant figures in a logarithm. For example, when the value of the hydrogen ion concentration has 2 significant figures, the pH should have 2 decimal places. So we'll kind of watch this as we go through. Remember, for the most part, if you're within 1, you're going to be fine. So in chemistry, we use the negative log of some quantity. Therefore, the concentration of hydroxide ions in solution is expressed in terms of pH. Now, I will say that for the most part, we're not going to talk about, if we're describing a solution, if we are ranking and comparing them, it's not going to be very often that we use POH. Normally, we use pH. Also, we can take the log of KW, and that equals 14. And so because of that, POH plus pH is equal to 14. So again, that's in your table. So what we're going to do is practice all this. I'm going to do, I think, 2 lines. These 2 here will be for homework. Practice these so that you know how to put these in and out of your calculator. That's really important. And I'm going to show you on these calculators, because this is what we have at school, how to do that. Okay, so we're going to start with this first one. This is a hydrogen ion concentration, and I want to find the pH. So what I'm going to do is I am going to take the negative of the log of whatever it is, 2.5 second EE minus 5. Don't really need to put close parenthesis, enter. Now, when we want to do sig figs, how are we going to do that? So we've got all these numbers here. How many sig figs do I have here? 1, 2. For pH, you start at the decimal and you move to your right. 1, 2. You don't worry about the number on the left of your decimal place, only here. So this is going to be 4.60. Okay. Now, if I want to find out my hydrogen ion concentration, remember that I can just take this, use the autoionization of water and the constant 1.0 times 10 to the minus 14, and I can solve for this one. So this would be 4.0 times 10 to the minus 10. So let me go this way. This number 1 is a negative log of 2.5 times 10 to the minus 5. And then number 2 is going to be the concentration of OH minus is equal to 1.0 times 10 to the minus 14 divided by 2.5 times 10 to the minus 5. Now for this one, I can either take 14, so let's do, for number 3, I could do 14 minus the pH. In that case, I would have 9.40, or I could take the negative log of this. Now, this is very important. When we determine whether something is acidic or basic, we always use the pH only, not pOH. Always the pH. If it is below 7, it's acidic. If it is above 7, it is basic, right? So we are going to take this number. This is below 7, so this is considered to be acidic. I could go through and do the same thing. Here's pH. Let's go backwards and find this. I'm going to call this 4. Now, the way that we plug this into our calculators, we need to take the inverse log. Okay? So, I'm going to hit clear. And what have I got? 7.92. So, I'm going to take this right here where it says log. You're going to use this 10 to the x. This is the inverse log. So I'm going to go second log, and you should get this. Remember, it's second log of the negative pH. What was that again? 7.92. Enter. That has got a lot of zeros on it, right? So I've got 1.2 times 10 to the minus 8. Now, if I had more digits here, I would then go up here and say, well, I've got 2 digits past the decimal point here, so I only need 2 here, but that's all I've got. So I'm going to put this as 1.2 times 10 to the minus 8 molar. So number 4 is 10 to the negative 7.92. All right, once I have all of that, again, I can just find my hydroxide concentration by using my autoionization of water equilibrium. I can find pOH by subtracting from 14. But remember, we don't look at that when we determine whether something is acidic or basic. We're always looking at this. This is above 7, so I'm going to call this basic. So I'm going to kind of do all of these. I'm going to fill these in for you. It's a good idea to make sure you can do the inverse log. That sometimes is a problem for students. You will get practice with this with the OWL, so you will have that as well. But this is not a bad idea to go through and work these. And then this is, notice 2 point, this is basic, this is acidic. Okay, now we can determine whether something is acidic or basic by looking at the pH. But let's look at some other ways we can determine what the pH of a solution is. Now, some of this you're going to be doing in the lab. For one thing, we can use what's called a pH meter. Okay? Because here's what's important about pH. pH tells us what the concentration of hydrogen ion is, and that's in our equilibrium expression. So we're going to use this to determine this, but in the laboratory, I can't measure this directly, but I can measure this. I can use a pH meter. Basically, you stick a probe in the solution, it gives you a number, and it tells you exactly what the pH is. I can use indicators. We're going to do this next. And I can also use, well, I'm going to put this in your pH paper. Right? So let's look at what this means. Here are some ways to do this. We've got litmus paper. It turns red to blue when it's basic, blue to red when it's acidic, an indicator, a pH meter, and there's also this paper called Hydrian paper, and it will tell you exactly what the pH is. And you're going to do that in your simulation. Now, we can also use indicators. Now, indicators only turn colors. Way to think of this is pH can change the way electrons flow inside molecules. And so when you change the pH of some of these dyes, they change their color. And so I can use these to determine what the pH of my solution is by putting these indicators in there and then looking at what the colors are. So let's do a couple of these. The first one I'm going to do is number 1. It turns orange and red. All right. So with methyl orange, it turns orange, and with methyl red, it turns red. So if I look at this, with methyl orange, it turns orange, right here. And with methyl red, it turns red. So it's kind of right in here. I would call that about a 4. Right? Next one, let's do another one. Let's do this one. With methyl red, it turns orange. With bromothiamyl blue, it turns yellow. So I look at this. With methyl red, it turns orange, so I'm right here. With bromothiamyl blue, it turns yellow. So I'm kind of right in here, which is around a 5 or a 6. This is orange. I'm going to call that a 5. Okay. And I'm going to do 2 more of these. I'm going to use blue and colorless, bromothiamyl blue and phenolphthalein. You've used phenolphthalein if you did labs if you're a senior, you did the labs with that. So bromothiamyl blue is here. It turns blue with bromothiamyl blue, and colorless right in here. So we're right in this range right here. That I would call an 8. So we're going to put 8 here. And then last but not least, you can see how combining these indicators is important, because if you look at this, if I just say blue, it's going to be blue from here on out. So I need another indicator to come from this end. So we're coming one indicator from this end, one indicator from this end. So let's look at the next one. Phenolphthalein turns pink. Now it's going to be pink all the way out here. But I'm in the yellow-orange range, so it says orange, for alizarin yellow. So that means I'm stopping here. So in that case, that's going to be an 11. So that's why we have to use a combination of indicators to show what the pH is. So again, and we're going to be doing all of these methods in order to determine the pH of different solutions in the laboratory.